Welcome to Mrs. Z's Chemistry. In this lesson, we are going to learn about something called Le Chatelier's principle. If we have a system that is at equilibrium and we apply a stress to the system, or in other words, we disturb the equilibrium so that it is no longer at equilibrium, the system is self-correcting. This is what this principle says. This means that nature will work to get the system back to equilibrium. We are going to look at each of these three different stresses that can be applied to any system at equilibrium. The first one we're going to look at is concentration. Concentration means molarity, which is the moles per liter. It's the amount of the substances that we have in the system. So when we stress the equilibrium, we are either adding or removing a reactant or a product. If a substance is added to the system at equilibrium, that is part of the equilibrium reaction, the system reacts to consume some of that substance and it shifts the equilibrium in the opposite direction. If a substance is removed from a system at equilibrium, then the system reacts to produce some of that substance that was removed. So let's look at some examples. We have this reaction. Diatomic nitrogen reacts with 3 moles of diatomic hydrogen to produce 2 moles of ammonia, or NH3. So what happens if you increase the concentration of nitrogen? So imagine we have all 3 of these substances in a closed container. There's no segregation in a closed container separating products from reactants. The NH3 doesn't know that it's supposed to be a product. It just exists in this system at equilibrium. Same with the reactants. So if the scientist decides to inject into the system more nitrogen, then you can think of this as the system has been supplied the ingredients to shift the reaction or have the forward reaction be produced. So then the nitrogen is going to be used up and more NH3 gets produced. So we say that this system shifts to the right. Shifts right, or more specifically, it shifts towards the products. And this is to get the ratio to products, from products to reactants, back to the equilibrium ratio. Now let's imagine, what if we have, again, all 3 of these in the system, in a closed system, and if we are to take out or somehow consume just some of the hydrogen. The equilibrium is now disturbed. The ratio of products to reactants is no longer that equilibrium constant value. And so the system, nature, is going to shift the reaction left or towards the reactants to produce some more of the hydrogen that was removed. So now what if we increase the concentration of the product, of the NH3? Well, now we have been supplied the ingredients necessary for this reaction to shift left, to consume that excess NH3 and turn it into reactants, so that the ratio of products to reactants is back to the equilibrium ratio, or the equilibrium constant. So you can pause the video here so you can study these responses and write down them in your notes. All right, so stresses due to pressure are only going to affect the reactions that are gaseous. So if you have solids, liquids, or aqueous substances in the reaction, the pressure is not going to affect it and it's not going to change the equilibrium. But if you have even just one gaseous particle in the reaction, then the pressure, changing the pressure by either squishing the container into a smaller volume or expanding the container into a larger volume, that's going to affect the pressure and that's going to disturb the equilibrium. So if the pressure is increased on the system by making the volume smaller, then the reaction will shift to the side that has the least amount of moles. You can imagine this, we are condensing the particles. Yes, the particles are probably going to be a little bit larger, but because we have more atoms in them, because we're condensing the number of particles, but there are still a huge distances between each particle, that the size of the particle is negligible. So the fewer the gas moles in the system, then that decreases the pressure back to a normal pressure. In the opposite way, if the pressure is decreased on the system, then the reaction will shift to the side that has more moles. We can count the amount of moles on the product side versus the reactant side by counting the coefficients on only the gaseous particles. So in this example reaction, all three of the substances are all gas molecules. They're all in the gas phase. The reactant side has 1 gas mole of nitrogen and 3 of hydrogen. So there's a total of 4 on the reactant side. And because of this coefficient on the product side, there's a total of 2 on the product side. So we have more moles of gas on the reactant side in this example than we do on the product. So in the sample problem, what happens if the pressure is decreased? Nature's going to want to increase the pressure back to normal, so it's going to shift towards the side with more moles. So it would shift towards the left. And then the opposite is true for this problem. What happens if the pressure is increased? That means nature will want to decrease the pressure back to a normal pressure, which is going to shift to the side with fewer moles, which in this example is to the right. You can pause the video here so you can study these responses and write them down in your notes. So what if the pressure is increased on this system where the moles of gas are equal on both sides? We have 1 mole here and 1 mole here, so that's a total of 2 on the reactant side. Because of the coefficient on the product, we have 2 also on the right-hand side. And so if the system is increased, the pressure is increased, nature would want to decrease that pressure, but shifting one direction or the other is not going to help. So nothing actually happens. The entire system just has to exist under more pressure. It just has to deal with it, and nothing can change. In the same way that if the pressure had been decreased on a system where they have the same amount of moles on reactant and product, then the whole system would just be under less pressure and nothing happens. We can add heat to a system at equilibrium by placing the closed system or the closed container on a hot plate or over a Bunsen burner. We can also remove heat from a system at equilibrium by placing the container in an ice bath. You would place the closed or sealed beaker or Erlenmeyer flask directly into a bucket full of ice, so that removes heat from the system. This will disturb the equilibrium system, and nature will work to get the system back to equilibrium. The direction in which the system will shift depends on if the reaction is an exothermic reaction or endothermic reaction. So heat is released in exothermic reactions, if you remember from our thermochemistry unit. This is the same as saying the heat is being produced on the product side. Heat is absorbed in an endothermic reaction, so you can imagine heat is one of the reactants. It is required for the reaction to move in the forward direction. When the temperature of a system at equilibrium is increased, the system reacts as if we added a reactant to an endothermic reaction or a product to an exothermic reaction. The system then shifts in the direction that consumes the excess reactant or product, which in this case would be the heat. Another way to describe an exothermic reaction is labeling the delta H, this right here, which is the change in enthalpy or change in the energy of the system, as negative. A negative sign means the reaction is releasing or losing or producing the heat. Heat is absorbed in an endothermic reaction, so it's the same as describing the delta H as positive, because in endothermic reactions, the energy is absorbed or gained or used as a reactant in an endothermic reaction. So for example, for this reaction here, we say that 250 kilojoules of energy is released when A and B react and turn into C and D. 250 kilojoules is absorbed, though, when we go in the opposite direction, when C and D react and turn into A and B. This should be written as B. So going back to describing this exothermic reaction as writing the word heat as if it's a product, so we have whatever the substances are here, and then we say plus heat, that means the substances are being produced along with heat. the delta H is negative, and when we increase the temperature, so we place this exothermic reaction over a Bunsen burner or over a hot plate, this results in more reactants. The reaction is going to shift left because it needs to use up the heat, the excess heat, and it shifts left. That means we now have more reactants at equilibrium than we do products because heat is not a part of the equilibrium expression. We still just have the value of the products, the amount of the products over the amount of the reactants. Heat is changing the ratio at equilibrium. Therefore, the K value here is going to decrease because reactants is in the denominator, dividing by a larger number, and with a numerator that is smaller, K becomes lower. But if we decrease the temperature on an exothermic reaction, this results in more product, because if we're taking away this reaction, this product here of heat, then the reaction is going to shift to the right to replace that heat that was removed. And this then creates more products at equilibrium. And so the ratio is skewed towards products, and this increases the K value. Now let's look at the endothermic examples. Endothermic reactions have heat on the reactant side. Delta H is positive, and so when we increase the temperature, this results in more products because we are supplying the necessary ingredients to shift towards the right or towards the products. Because our K is still calculated products over reactants, then this increases the K value because we have more numerator, namely the products. Decreasing the temperature, though, on an endothermic reaction is as if we are taking away a reactant, and therefore the reaction will shift towards the reactants in order to replace the heat. And this also means we have more reactants, which is more denominator. So this lowers the K value of an endothermic reaction. Let's look at this, these words down here. A temperature change is the only stress or disturbance that changes the value of K. Changing pressure or changing the concentration changes the numbers, it changes the amounts that we have at equilibrium, but the ratio of products and reactants will still be the same. But only a change in temperature will change the value of K. This is why in equilibrium problems, when it states the K or equilibrium constant value for a reaction, it will always say you're at a certain temperature or even give you the specific temperature, like 500 degrees Celsius. You don't use the temperature in the problems, but it's stating the temperature because the K value is dependent on what temperature it is. When a system is no longer at equilibrium, the ratio of the concentration of products over reactants won't equal the equilibrium constant, K EQ, anymore. When we calculate the ratio of products to reactants not at equilibrium, we call this the reaction quotient, or Q. It is calculated the exact same way as an equilibrium constant K, but we call it a Q when the system is not at equilibrium, or if we just don't know if the system is at equilibrium or not. So it's still products over reactants, and any coefficient is turned into an exponent, but this is when it's not at equilibrium. The values we're plugging in are not equilibrium values. After calculating the Q, given the concentration values that were given in the problem, we can then compare this calculated value of Q to the value of K that is also given in the problem. So then if K is greater than Q, nature will make the reaction form more products, and the reaction proceeds from left to right in order to increase the value of Q up to the value of K. Because once K and Q are equal to each other, then that means the reaction system is at equilibrium. But if the K value given in the problem is less than the calculated Q, then nature will make the reaction form more reactants, and the reaction will shift to the left in order to decrease Q down to the level of K, because nature wants K and Q to equal each other. So let's do an example problem. At 100 degrees Celsius, the equilibrium constant, this is the K, for the reaction given here, has a value of 2.19 times 10 to the negative 10. Are the following mixtures of COCl2, CO, and Cl2 given here at 100 degrees Celsius, are they at equilibrium? If not, indicate the direction that the reaction must proceed to achieve equilibrium. So, this is system A, and we'll see, or this is a scenario A, and we'll see the examples of B and C in a moment. But first, we need to write out the K expression. We have products of CO and Cl2. There are no coefficients, or at least the coefficients are 1, so we don't have any exponents here. Products divided by reactants. We don't know, so we know the K value is equal to 2.19 times 10 to the negative 10. So that's at equilibrium. But we're going to check, and we're going to plug in all of these values. So since we don't know if this is at equilibrium or not, we're going to call this a Q. So we're going to be calculating Q. When we plug in the values, the value for carbon monoxide is 3.3 times 10 to the negative 6. The value for Cl2 is 6.62 times 10 to the negative 6. And then the denominator is the COCl2 value at 2 times 10 to the negative 3. When we calculate this then is 1.09 times 10 to the negative 8. Pause and type this into your calculator to see if you can get the correct answer, because this sometimes is tricky to type into the calculator correctly. So we can compare the K value given in the problem up here at 2.19 times 10 to the negative 10. 2.19 times 10 to the negative 10. That is a less value, lower number, than the Q we just calculated of 1.09 times 10 to the negative 8. So this greater than less than sign here, it is pointing in the left direction. So that means the reaction will form more reactants in order for Q to then equal K. Because reactants are in the denominator. We need more reactants. We need this value to get lower down to K, because nature wants the value to be at K. So the scenario of system A here is not at equilibrium. Let's look at system B and C. Plug in these values in the same way that we did for scenario A and see if you are at equilibrium or not by comparing your calculated Q's to the K value. And here are the answers.